Thank you all for coming today. So right now we'll start talking about how we approach the problem of code provenance at Uber. My name is Debo. I'm a software engineer on the application security team. I was born in Mordor and raised by wolves.
And I'm Matt. My career can be characterized as a series of escapes. Most recently from San Francisco, I live in Santa Barbara and work at home, where these are my two assistants.
And hey, I'm Tony, and I'm gonna change that first bullet. I recently got to spend a couple days in Hawaii, so I actually wish I was born and raised in Hawaii because it's awesome. Yeah. I have not escaped SF yet. I still live there, where I am constantly terrorized for food by this face, my pup. Oh yeah, for sure. Can you guys hear me? Cool. All right, so we're here to talk to you guys about code provenance, right? And before we jump in, we're gonna take a look at the agenda. So we'll first start by defining kind of what code provenance is and what we aim to solve. And then we'll dive into a bit of a bit on the software development process at Uber, mainly to kind of give you guys a base onto some of the work that we put in place in that process. And then we'll dive into some examples, commit signing and third-party dependencies, to kind of get all the fun learnings and experiences we got from that. And then we'll wrap it all up by kind of taking a look on how we utilize these foundations in order to build and chain enforcements all along the way, all along the software development lifecycle. And of course, we'll leave some time at the end for some Q&A. Cool, let's dive in. So code provenance. What is code provenance, right? What is this thing that we're talking about? So we kind of like to begin by defining it with words before we actually dive into defining what it means with slides. So to us, code provenance is ensuring that we have a verifiable attestation of the origin of all code running in production so that we can have a root of trust as we kind of move forward to define and enforce a collection of policies throughout the different stages of the software development process. You guys get all that? All right, we're done. That's it. So let's talk a little bit about what we're kind of protecting against when we're talking about code provenance. Like, what are we protecting against here? Well, checking for vulnerable and or unreliable or buggy code is kind of standard, right? And it's a small subset of things and reasons for why you want code to go through a process before it actually goes and makes it into production. So at code review time, this is kind of our first time and first chance to check for errors, check for bugs, check for vulnerabilities, right? Both through through peer review, or robots through automated analysis. We can check the diff to make sure that no new issue has been kind of introduced. At CI testing time, we can ensure that the code has not regressed, both in logic and reliability, and make sure that the diff is stable. Security unit tests here can add some checks for security vulnerabilities. When code lands on the repo, more broad stroke analysis can be done, like checking for CVEs or more advanced analysis. At build time, analysis is run on the built artifacts, like a container, to weed out kind of things and vulnerabilities that have been introduced at that time, like insecure configurations or insecure system libraries or frameworks. Integration tests after that gives us another round of stability and reliability testing. And of course, at deploy time, we do a final check of authenticity, integrity, and security attestation before we actually deploy the built release. Of course, this is not a catch-all for all mistakes, right? But at least gives us some level of assurance that we're catching some known issues. So the idea of code provenance is to kind of protect us from a number of different scenarios where both malicious and non-malicious code is kind of shortcutted. They're shortcutted through these checks. right? So first, we have kind of what we call a lazy or shortcutting insider. And this is someone who doesn't really, they're not really malicious. They mean well, right? But they kind of want to just get past the tests, past the reviews, past the lint warrant, and they don't care about that stuff, right? They just need to get their code into production as soon as possible. Policies be damned. Next up, we kind of have our malicious insider, someone who has engineering access, and unlike the non-malicious, this person wants to do some harm, some malicious harm, and they want to sneak code into production. They may attempt to try to sneak code and make it look like someone else has submitted this, or they might just want to get around some review requirements. They kind of want to get malicious code into production without raising any alarms. Next, we have an outsider who has control of maybe an engineer's laptop, right? Similar to the malicious insider, they want to use this access to put malicious code into production without raising any alarms. And then finally, we have an outsider who may attempt to directly attack the build and deploy infrastructure. Okay, so what about the flip side? What are we actually gaining when we add code provenance, right? What are we enabling? Well, once all is said and done, we should effectively have a verifiable chain of custody for every bit of code that ends up in production. Ideally, we can sample any sample of running code and know that it came from a specific authorized build, and that authorized build was constructed from a specific set of commits, each of which has a known and verifiable author, each of whom is an engineer with the correct level of access to actually make that change. And in the event that some code or malicious or anomalous code does end up in production, our security response team should be able to trust the breadcrumbs, the metadata that we put in place in order to kind of learn what happened, kind of figure out that story all along the way. In addition to all that, we should be able to be assured that nothing made it through our entire software development process without verifiably passing any of the checks that we've put in place along the way. For example, if we had a blacklist of third-party dependencies that we did not want in production, no developer or an engineer should be able to add that into, they should not be able to get that all the way into production. So a quick disclaimer though, before we actually move forward into defining some of the things that we've done. This journey is not complete, and although we have a roadmap, we have an overall vision on this, there's definitely work to be done. So we're getting to it, or better yet, come help us build this all out. With that, I'm gonna pass it on to Matt.
All right. So everyone in the room probably has a sense of what software development works, what a software development process is, but I want to go into some of the details here for what this looks like at Uber specifically. So if we start with just one product for now, thinking about, for example, the Uber iOS Rider app, which is probably the app that most of us are familiar with in the room, we go through what looks like a fairly standard development workflow. You go ahead and write some code, you test it locally, you get your code reviewed, you make sure it passes in CI, and you land the code. This eventually triggers a build of a release candidate that will include the new code, and then this will undergo some integration testing and dogfooding. This ultimately ends up in an app that gets released in the App Store. So bringing this back to what Tony just talked about, what we want to do here is increase our assurance that the code that lands in this production release is in fact the code that was supposed to have landed here, and that we have all this metadata along the way so we can understand what happened and any policies have been met along this process. So all fairly straightforward so far. But that's just one app, right? So that's our iOS app. Turns out we also have an Android app. And so this same diagram looks fairly similar. Write your code, get it reviewed, etc. But now we're writing the code in a different language. We're doing code review with slightly different policies. We have CI testing in slightly different CI infrastructure. The release gets built through a distinct process, and on and on and on, right? This is actually a separate process that has grown up independently of the first one that I talked about. Still maybe fairly straightforward, but now that's just two of the apps, right? We also have many web services. So one of these is the Uber web service with its own distinct process slightly different tooling, different language, different team that owns this process. And this kind of goes on and on and on. We have all these different processes for all these different applications and services, all of which in many cases have grown up independently from each other and are managed by different teams. Many, many times over. So the key word here is heterogeneity, right? We have all these different applications with all this different tooling. And so I like to think of these as special snowflakes. Different processes, different teams, different norms. And so if you start with just thinking about one of these services, let's say it's the Uber iOS app, the one I mentioned at first, and we start to try to think about what this looks like holistically, go ahead and take the iOS app, now multiply by 32, because we actually have 32 distinct iOS apps. Go ahead and double it, because we have just as many Android apps. Now go ahead and add all the back-end services, and we quickly run out of space on the slide. And so when we take a step back and zoom out, this is what you get. This is the software that makes up the Uber machine, something like 64 mobile apps and 4,000 services. Well, so what? What's the point of all of this, right? The idea here is that we need to be really thoughtful about how we can do something general enough that will work for all of these different special snowflakes, all these different applications, all these different teams. We have to find some point of commonality or some choke point, something that these have in common so that we can create this general solution for code provenance. And we have to do so in a way that's thoughtful enough that we don't break production systems or upset too many of our engineers. And so in our experience, off-the-shelf solutions generally don't work. Any solution that starts with, well, why don't you just, has been a non-starter in our experience. So I'll attempt to drive this point home a little bit with a concrete example of commit signing. So many of you may know already that Git has built-in support for signing your commits. And the way this works is that it uses GPG keys. Now, in our infrastructure, our developers have a different set of keys. They don't have GPG keys. They have short-lived SSH certificates and all of the infrastructure that goes along with that. So these are great because they're actually renewed approximately every 24 hours using multi-factor authentication. So we have sort of this better infrastructure around key management for all of our developers, and it's already rolled out. So we're stuck with this interesting choice of resolving the key distribution problem for a new set of keys that I would argue is actually worse than the set of keys our developers already have, or, and in that case, using the built-in commit signing that Git provides, or using this better set of keys that we have and implementing our own custom commit signing solution. So as you may guess, we opted for the latter. The commonality that we use in this case that I mentioned before is that that all of our developers have this verifiable cryptographic identity via these SSH certificates, and fortunately, all of our repositories use Git. So we take advantage of these two things in common to build a base for all these special snowflakes for all these developers to sign their commits across these different repositories. But I'd like to take a step back before we take a couple steps forward. So why are we even signing commits? What is this all about? So commits are just metadata, commit identity is just metadata that exists inside the commit. So you have this author field inside your commit, and that says who authored the commit. But how does this association actually happen? Well, it's just a configuration setting. You can send a different name into your commit message or into your Git configuration. And so it's actually fairly easy to create a commit that says it was created by someone else. And so thinking back, if we're trying to understand who committed something, this is not the metadata we need, right? What we need is metadata that is tied back to some cryptographic identity that our developers have. So how do we actually go ahead and sign commits? We have this fork in the road. We can do this either at the server side, where our developers authenticate to the Git server, push their commits, and the Git server then knows who authenticated via SSH and writes out some metadata about who did that. Or we can do this via the client side. Use those SSH certificates that I mentioned, and developers create commit signatures sort of alongside of the commits they create, and then go ahead and store these somewhere. So these are two very different paths with different challenges and that affect a different set of systems. In our case, on balance, we decided that it'd be easier to do this on the client side, and it also is more parallel to the sort of native commit signing that Git has that I mentioned earlier. So our high-level approach is to use Git hooks, pre-commit and post-commit hooks, to actually do the signatures, and then to store the signatures in this feature that Git provides called Git Notes. And Git Notes are this functionality for storing metadata about commits, but outside of the commit itself. So we create the signatures when developers create their commits, we store the signatures in Git Notes, and then we have yet another commit hook, a push hook that will push the signatures alongside the actual commits. And then to top this all off, we distribute this configuration to tell it to use the hooks and the hooks themselves with Chef to all of our developer endpoints. Fairly straightforward, right? What could possibly go wrong? Special snowflakes, of course. So we ran into conflicting Git hooks for a vast minority of repositories. The most common example we saw here was repositories that use a client-side commit hook to format commit messages in a very specific way, so that they all contain sort of the same set of metadata and they all look the same in their format. So initially our thought was, okay, well, this should be no problem. Git surely provides some mechanism for us to run multiple hooks and to say which repositories they should run on and in what order. This turned out not to be the case. So this was some sub-problem that we had to go solve. And we did so by developing what we call a Git hooks middleware. So again, this was something that we distribute to our endpoints via Chef, and it manages a set of distinct Git hooks. It uses configuration options to say which hooks run on which repositories. So we have our global commit signing hook that runs on all repositories, and then we have these special snowflakes that get to run their hooks just for their repos. Okay, so at this point we've rolled out our commit signing solution. We've deconflicted the hooks with the existing hooks that we found along the way. All these hooks are centrally managed, rolled out to all our developers. They run in a well-defined order on the correct set of repositories. So we're done, right? What else could possibly go wrong? Special snowflakes. So we discovered amongst the thousands of repositories a single server-side hook in one repository that caused problems for us. And so this was doing a very specific thing. It was a hook on the server side that was checking a configuration file to make sure it was in the right format for every single branch pushed to the origin. And so what this meant in our case, based on how Git Notes actually work, is that when our notes ref was pushed to origin, this looked to that hook just like another branch. And so it would look at our Git Notes containing all our signatures. It would, of course, not find this configuration file at all, because this is not the code repository in this case. And it would fail every single push of signatures, which in turn would fail every code push. So this was an interesting case because the bug was actually in the server-side hook, but the bug didn't manifest until we used this Git Notes feature that we decided to use. So what's the takeaway from all this? We learned a bunch of lessons here. The first one is that nothing is initially as it seems. We sort of realized that we can't necessarily predict in advance all of the myriad things that are going to go wrong in such a heterogeneous environment as ours. And so the thing that works for 90%, or in some cases 99% of your developers and of your repositories will sort of catastrophically break the remainder of them. And so because we knew that we couldn't predict everything in advance, we knew we had to have a plan. And so this plan was sort of threefold. The first item here is making sure we had the ability to deploy incrementally so that we could roll out to just a test cohort and then to just engineering security, 5% of engineering, 10%, etc. And the great thing about this is that it lets us discover these problems that I mentioned previously and others, but in such a way that we don't break everything for everyone all at once, and we don't take on the support burden of having to fix everything all at once. And so related to this is the idea of just being ready to turn everything off at the drop of a hat. So we had this built in to be able to just shut this off instantly via Chef for when we discovered these problems. We could then go sort of take our time a little more to address these problems and then turn it back on for everybody. And then finally, the third prong here is empathy. We got a lot of mileage out of empathizing with our developers, right? Developers don't care that your fancy new tooling works for 99% of the company. They don't even know in many cases. All they know is that you broke their computer. And so, in many cases, just apologizing, explaining to them what this effort was, what we were doing, why it broke in this particular way, and then moving on to the next thing was really the way to go. And so finally, what you see up here is that computers are the absolute worst. This would have been easier if the whole world was devoid of software. Of course, we imagine sort of breaking our computers, burning us to the ground. When we sort of stepped back and reflected on these feelings, we realized that this all would have just been a lot easier in a less heterogeneous environment. And so the lesson to take away from this is that, and especially for companies earlier in their life cycle than ours or smaller than ours, if you have an opportunity to reduce the set of supported technologies, set of supported languages, set of supported build infrastructure, etc., take it. It will pay dividends. And with that, I'll turn this over to Debo to talk about third-party dependencies. Thank you.
So, thank you, MSF. So, a lot of the code that we run at Uber is open source third-party software, right? And this ends up being a majority of the software that runs in our production systems. Given that it should amount to us putting at least the same level of security stringencies when it comes to using these third-party libraries, right? But unfortunately, that is not the case, and usually we can pull in third-party dependencies with essentially little to no oversight. So what exactly is the risk from these third-party libraries, right? Third-party software can pull in malicious or vulnerable code, and these are some of the examples that we have seen in the recent past. And a part of this problem is also actually understanding where this third-party software is coming from. Is it really coming from the trusted registry that we think it is? And this essentially leads to the problem of having a verifiable attestation. So in order for us to understand how we can secure these dependencies, we need to break the problem into two parts. So the future-facing efforts would be essentially covering whatever dependencies will be introduced in our infrastructure from here on out. And then the existing work would tackle all the dependencies that we already have running in our infrastructure. So for the future-facing scenario, all newly introduced dependencies from a global context will undergo a lightweight vetting process. We'll have some policy backing this, which would cover things like high plus CVEs, maybe some package blacklists, some licensing constraints, and so on. Then for all newly introduced third-party libraries from a repo local context, we'd want to start assigning internal owners. Why is that? Whenever we actually encounter a known vulnerability, this would help us with our remediation process. So now let's get a little bit into how we can implement something like this. So in our system, we have developed some pull request type hooks. What do they do? Whenever there's actually a change in the requirements manifest file, which ultimately becomes, okay, so someone is trying to introduce a new dependency. We'd want to find out if this dependency has already been introduced at Uber before. So we have a little inventory system that tells us, okay, if this is a new dependency from the global context, let's kick off a new vetting process. Alternatively, if this is a new dependency from the repo local perspective, the pull request author essentially becomes the owner of that dependency for that repository. And now we also make a note of it in our inventory system. With this, all of our new third-party dependencies are somewhat accounted for. And we also have a level of verifiable attestation. Okay, so how can we, for our existing dependencies, we have two approaches that we can take on. One is the process of greenkeeping. So we try to keep all of our dependencies updated to the latest versions at all times. But there's a slight problem with this. As Matt had mentioned, we have 4,000 microservices and thousands of dependencies. And it really doesn't, at this size, we can't scale our team to keep all of these dependencies updated reliably. Alternatively, we can also make targeted library updates. So whenever we encounter a known vulnerability, forward that to the product engineering team and then have them be responsible for updating the library version. And there are also some vendor companies that are working in this problem space. So with this, it seems fairly easy, right? But to understand this a little further, we need to look at the composition of a backend service. A backend service usually takes a direct dependency on multiple third-party libraries. These libraries then pull in multiple other dependencies, and this keeps going on and on. So what if we find a known vulnerability in one of these third-party packages? This in turn would taint whichever dependency was responsible for pulling it in, and this keeps going up the chain. So, okay, we have found a potentially vulnerable library now, but a vulnerability in a third-party package does not necessarily manifest itself as an exploitable vulnerability. Let me give you a little example. So, if we have a URL parsing vulnerability in some package, but if the first party code is passing that vulnerable library a static URL, this does not necessarily manifest itself as an exploitable vulnerability to the world, right? And given our scale, we can't just forward all these hundreds or thousands of issues to the product engineering teams and wish them luck. So, a good question to ask here is user input actually ever touching a vulnerable library? So in the instance to your right, you'll see that user input touches a potentially vulnerable library, but that does not end up hitting an actually vulnerable library. But in the case to your left, we'll see that it actually does. So it's clearly not very straightforward. Till now, we have established that we have backend services that have direct dependencies, which have indirect dependencies. Some user input will just touch the first party code, some of it hits a direct dependency, and some of it hits an indirect dependency. But the real question we need to ask here is what the vulnerable function is and whether user input is actually ever touching it. So there are some vendor companies working in this problem space right now. They call it advanced analysis, which ultimately is a combination of two things. So from the static analysis perspective, it's using control and data flow graphs to figure out whether a vulnerable function is ever being called. And from the dynamic analysis perspective, they have some code instrumentation to also figure out when a vulnerable function is actually being called at runtime. But unfortunately, none of these solutions panned out in our environment for multiple reasons, so we had to come up with our own. When you have a vulnerability, the thing we usually care about is the severity associated with it, right? And severity is the product of risk, likelihood, and impact. And in our environment, we can make justified arguments about risk and likelihood, but impact is something we start to struggle with. What exactly is the vulnerable function, and is the first party code actually calling it? So we actually went out and manually evaluated a whole bunch of findings. And after exactly this amount of time, we made an observation. So the deeper in a dependency graph that a vulnerable library would appear, the less likely was it to be used in an exploitable vulnerable way. With this, we developed a heuristic. For now, we'd only care about libraries that were less than 3 levels deep in the dependency tree, And we'd also focus our efforts on just critical and high severity issues. Admittedly, this process still has a lot of false positives, but this leaves us with a triage process that is essentially more manageable at scale. And this is kind of the path we are taking right now with respect to our third-party dependencies. And with that, I will hand it over to you, Tony.
All right, I'm going to try to wrap this up by talking a little bit about how we're taking these foundations and kind of moving it forward in a meaningful way, right? So far we've covered up to committing code, and as we know, there's a bunch of different steps between committing code and actually deploying an application. There's building the application, there's testing the application, there's actually going through the deploy process of deploying that application. And these in-between steps kind of open up a lot of surface area for things like code injection or injecting code or third-party dependencies within that surface area. So in order to truly ensure that the code that is running in production is the same code that we've approved, that has been approved, we need to make sure that we, one, set up enforcements all along the software development process, and we chain those enforcements in a way where it starts with the approved commits all the way to production. So let's talk a little bit about how we chain results. So code is written by an engineer in one or more languages and is packaged into the form of a diff or a pull request or whatever you're using, and these are committed to repositories. We'll call the sum of all these commits that end up in a repo a commit box. This commit box is created with a theoretical stamp that ensures us that this is coming from an approved author, i.e., it has a commit signature on it. Commits are then landed on a repo and given a SHA to represent their exact state. This we'll call the repo box. The repo box creation process has its own set of checks before creation, right? Which includes security scans, but it also includes checking the commit box stamp to ensure that this is coming from an approved author without actually having to do that check. One or more of these gets built into and packaged along other things like system packages, frameworks, etc., into a box that represents the application itself, called a container, or in iOS or Android case, an application package, an IPA, or an APK. But we'll just call it a container for simplicity. So it's kind of weird to call this a container box because a container is kind of like a box, but we're just going to call this a container box anyway and deal with it. This container box also has its own set of checks, right? Which includes checking the repo box stamp, which ensures us of both the fact that it meets security policy and that it's coming from an approved author without actually having to do that. This container box is then checked and then deployed. This chain of custody that actually routes back to an SSH key at commit signing time will enable us to inherit trust by kind of verifying just one layer deep in your nested boxes. So you kind of never have to ask the question because it's totally fine. You can trust nothing's bad in the box. All right. So I'm going to try to, another way to kind of drive this home is to kind of compare this to the OSI model and layers, right? The main attributes kind of that make it kind of similar are the fact that each layer has its own scope responsibilities, only really communicates one layer above or below, but still gets kind of those benefits because of the encapsulation and chaining that's actually happening. So I present to you the 4 layers of the code provenance model. The commit layer, which is in charge of approved authors, and identity, right? And it takes as input SSH keys and uses that to sign commits, ensuring that we have a form of identity connected to all code moving forward. The repo layer is where software analysis is run, and we find ourselves with commits as inputs. And from earlier, we know that commits holds a verifiable attestation of the origin of code that's being added via the commit signature. So the presence of a valid commit signature allows us to set up some enforcements based on policies to ensure us that the code that we're dealing with comes from an approved source. This, of course, doesn't assure us that the code is actually not vulnerable, so we still have to do some scans for that on both the app and third-party code, something that Debo discussed in his previous sections. But then the signature put on that repo at this state can verify both those things moving forward. The container layer is where OCI scanners are used to check for vulnerabilities in the operating system packages, frameworks, or configurations. This takes repos as inputs and inherits kind of inherits the attestations that come with it, right? Secure application third-party code, all the code that's introduced is coming from an approved author. And the signature associated to this container can be used to verify all that, and of course the fact that, of course to authenticate the origin of where this was built. And then of course, we have the host and deployment layer where the container signature is verified, which kind of inherits everything before the app actually gets deployed. So we go back to our big picture state of the Uber machine, where everyone is kind of their own special snowflake. And we zoom back into one of the services. So from all we've talked about what we've done in this talk, we can actually begin to see some guaranteed similarities, right? Some patterns that can actually bring some homogeneity in our inherently heterogeneous environment. We can see this by kind of walking backwards or peeling the onion, if you may, in our software development process. Because deployed applications, they're really just containers of some sort that have a signature to be verified. And these containers are known to be built by our build systems and known to be secure. Containers consist of repositories, right? Repositories that have secure code added through commits. Commits that we know come from approved engineers. And through that, we can guarantee code provenance of all the code that make up the lifeblood of the Uber machine. Thank you.